Hello, welcome. My name is Fred Mensik, and the presentation today is Stop the Spill, Save Salmon. In this presentation, I'm going to show how we have damaged these fish long before this time frame today. Here's a picture of the canneries working, the blue line, the canneries working down on the Columbia River in thousands of pounds of fish were canned. The commercial fishing and habitat loss reduced salmon abundance 97% by 1939. This is the canning process, the number of pounds of fish canned, and these are dams that were put up in the state of Idaho. All of that without fish ladders. Today, at this point, we're down here and people are blaming Lower Snake River dams because they don't understand the history of how we got here. 72 years ago, they knew what was going to happen. Forrest Hauk, fish biologist for the state of Idaho, said, "The controversial Hells Canyon issue doesn't look so bright. Either Hells Canyon Dam or the series of 3 dams will prevent the upstream passage of fish. At least there are no known successfully operated fishways over 100 feet tall. At the Lower Snake River dams, each of the fishways, each of the adult fish passage ladders is 100 feet tall. And they work extremely well." This is a study by the University of Idaho where they radio tagged fish at Ice Harbor and put them back into the tail race to see how many would get upstream to escape to the lower granite pool. As you can see in the circled number, it's 99.7% of the fish passed each project. That means the fish ladders were extremely efficient. And overall, the total was 99.2% of the fish passed from Ice Harbor to the lower granite pool. Lower Snake River dams are run-of-river dams. They are not major impoundment dams. Therefore, whatever water comes to the dam passes the dam. For example, if 100,000 cubic feet per second comes to the dam, it can be used for the turbines and spun for electricity, unless spill is required. If spill takes 50 kCFS, the turbines only get 50 kCFS. This is a loss of revenue. It does not mean more water. Flushing does not mean more water. It means a different distribution of water. So flushing fish, the term used for spill, is highly inaccurate. It's not more water. But if we flush fish or spill for fish passage, we have to realize that the fish are part of the water system. If we spill, there's going to be fish in that spill. The red line is the total spill. The yellow line is the number of fish bypassed. And as you can see, there are trend lines here. They're not exactly parallel, but they're very close, which shows a mathematical correlation. These numbers come from Fish Passage Center. I believe they're highly inaccurate because if you're only transporting a few million fish, then all the rest are being bypassed. And if these numbers were corrected, this number would be almost parallel with the volume of water being spilled. But what happens when you leave fish in the water? Roughly 50% of in-river smolts die by the time they reach Bonneville Dam. We have predators like walleye and bass. And if you go to any of these dams during the high spill periods, You'll find seagulls picking them up. The fish are disoriented by the spill. They dive down 60 feet in order to go under a spill gate. With each 30 feet, there's a 1 atmosphere of pressure increase. So they go down almost 2 atmospheres, come out of the gate, and the nitrogen in their system suddenly explodes, and they have what we call gas bubble trauma. And these fish are easily picked up by the seagulls right below the dam. So 50% die on their way to Bonneville. Fortunately, there's a way to get around that, and that's to transport fish. If we transport them in a barge, 98% survive to the estuary in a barge. The science supports transporting smolts. A NOAA report stated, transported fish return at a higher rate than migrants in the run. That was a 4-page report. That report was given to Fish Pasta Center. It took them 36 pages to respond to this report. In their response, they stated smolts that were not bypassed, and those are transported fish, return as adults at a higher rate than smolts that were bypassed, or rather in-river fish. A Patel report was done on barging, and they stated, we conclude that on a yearly average, it is better to transport both wild and hatchery spring summer Chinook salmon collected at lower granite. This report, printed in the North American Journal of Fisheries Management, stated that the weighted average of our within barge estimates was slightly over 98%, which comports well with assumed 98% survival value that has been presented in previous literature, and they go on to mention 3 other studies that support what they came up with. In the study produced by NOAA, it's presented a little differently. They show the wild spring summer Chinook in the river on the right, and the transported fish, the SARS, smolt to adult return, on the left. What group would you want to be a part of? This is for wild steelhead. The in-river fish are on the right, but the majority of fish that return are the transported fish. Barging works. That study by NOAA continues today, 23 years of research. And in it, Steve Smith is currently the biologist, and he presented the data a little differently. In bar graphs, the green is the transported, the blue is in river. As you can see, there are more returns from transport than there are from bypassed. So there are 2 options. One is to spill water versus barging smolts. In this graph, there are 2 lines. The blue line is spill. And as you can see, spill since 2001 continues to increase. The court order spill started in 2005. The red line is adult returns, and it is decreasing as spill increases. The spill is not improving adult returns. On this graph, there are 2 lines, and the blue line is pushed back 4 years. 1, 2, 3, 4 years. The reason for this is it shows the year fish were barged with the year 4 years later of their return. As you can see, there are 2 trend lines here, and both of them are almost parallel. which shows a mathematical correlation of the data. Why move the information back 4 years? QuickFix did a report, and in the report they showed that the 4-year-olds were the most abundant to return, the green line. We know that adult returns are linked to the number of smolts barged, and we know that 98% of the fish barged survived to the estuary. So why are we reducing the number of fish barged? Remember, these are important numbers over here. The number of fish barged is very, very low. So where are we headed with reduced barging? In 2018, we barged 5 million fish. That was reduced to only 3 million the following year, 2019. In 2020, we only barged 1 million, and in 2021, that was reduced to only 366,000. 4 years from 2021 is now this year, 2025. And we already have predictions of very low returns. The spill experiment has failed to increase returns. This graph shows it very well. The fish are not returning as a result of spill. It is a not flushing fish the way people claimed it would. And if we don't get them to the ocean by barging them, they don't come back. This table is very important. I wish I could hand it out to everybody. On the left here, we see 10 years of barging, and the average is 7 million fish. During that time, we were putting a lot of fish out into the ocean, and I call that priming the pump. By 2021, we had a very nice return of 500,000 fish. In 2005, we barged 12 million fish and had another 500,000 fish return. That priming of the pump continued, but we also started spilling here. So after a couple of years, all of a sudden you're going to find the number of returns starts to diminish. We went from 7 million fish transported on an average to only 2 million. And we went from 368,000 during this period down to 197. That's a decline of 46% in adult returns. The spill experiment has failed miserably. But imagine if we barge 7 million smolts for 6 years in a row. I want to thank you for coming today and listening to this presentation.